Today, I'm going to present our ICCV 2025 paper, Controllable 3D Outdoor Scene Generation via Scene Graphs. In this work, we use scene graphs as conditions to control the generation of 3D outdoor scenes. Now, I'm demonstrating the use of the interactive system we developed. First, the user needs to create nodes from the left toolbar. Be specific, they could drag the desired object nodes from the left toolbar into the main panel. After this, the user can assign approximate position for each object in the 3D space. We provide a position selection panel, which helps users select an approximate position for each object. Next, the user can establish appropriate connections between different nodes. Establishing a connection also implies that the two objects will be spatially close to each other. By clicking the Generate button, a 2D semantic map will be generated based on the scene graph designed by the user. And the user can then proceed to generate middle resolution scenes using the generated semantic maps, and upscale the scenes to high resolution based on the middle resolution scenes. That's the end of the demonstration. Currently, some controllable 3D generation methods use multi-view 2D images to generate 3D models. However, due to the complexity and interconnected nature of outdoor scenes, these object-focused methods are challenging to adapt for outdoor 3D scene generation. Additionally, there are works that generate outdoor point clouds using natural language descriptions. However, text-to-3D provides insufficient control over both physical constraints and spatial details. In this work, we propose a new control paradigm by utilizing scene graphs for controllable 3D scene generation. Our method is divided into three main components: the design of an interactive system, the generation of the bird's eye view embedding layout, and the conditional 3D scene generation using a diffusion model. We use the scene graphs as input to a graph neural network, obtaining the embedding for each node, and a global embedding by pooling all the node embeddings. In this process, we enhance the training of the graph neural network by incorporating two auxiliary tasks: edge reconstruction and node classification. Subsequently, our allocation module assigns each node a position in the spatial domain. The generated BEV embedding layout is then used in the diffusion process. First, a corresponding 2D semantic map is generated using the layout as a condition. Then, the generated 2D semantic map is used as the condition for generating the middle resolution scene. Finally, the high resolution scene is generated based on the condition provided by the previous stage. All of these operations can be completed using the interactive system we designed. The visualization results show that our method captures the scene graph information well and generates scenes that match the specific requirements. For example, in this case, the number of objects in each category and their assigned positions in the scene graph are accurately matched in the generated result on the right. Additionally, our results show that using the same scene graph as input, our method can generate diverse 3D scenes for each run. Although the generated 3D scenes are different from each other, the objects and their positions in these scenes largely remain consistent with the input scene graph. This also shows that our method does not simply overfit to the training data, but instead maintains both diversity and structural consistency. We also explored the impact of different training strategies on the quality of the generated scenes. We found that jointly training the diffusion model and the graph neural network, and then freezing the trained models and post-training the localization head, which is responsible for position allocation, gets the best performance. Quantitative evaluation also indicates that our method not only generates scenes that comply with the scene graph, but also achieves good quality in the generated scenes. In summary, we designed a framework that uses scene graphs to guide the generation of 3D outdoor scenes. We employ a graph neural network to transform structured information into compact embeddings that guide the 3D generation process. Additionally, we created a large-scale dataset consisting of paired 3D scenes and scene graphs for model training. Furthermore, we developed a user-friendly system to facilitate the creation of custom scene graphs by users. That's the end of our presentation. Thank you for watching.